Hi, in this lecture, I'd like to show you what it's like to explore the capacitance of a couple of conductors. So in this particular case, we're going to end up getting the capacitance of what's called a parallel plate capacitor. But a parallel plate capacitor is simply a pair of conductors where each conductor is a flat plate, and we're going to make sure to take these two flat plates and separate them with vacuum, right, which is the ultimate insulator, by a small distance. And so here's a picture of the setup. The separation is in the x direction. I've got a big flat plate on the left and a big flat plate on the right. And for the parallel plate capacitor, we're imagining both plates as having the same area. And we're going to make them parallel, right? So from the side, it also kind of looks like this. This is a simpler drawing. This drawing over here on the left has some perspective. I just want to show you that they're two-dimensional surfaces, right? Two-dimensional plates. So each is of area A, and the separation is D. And what we'll say is that small separation D means that essentially, if we imagine A, like the area, as being, say, a width times a length, right? So L times W is A. This just means that D is really small compared to either the length or the width, right? This is what's meant by small separation. And the reason why we want a small separation is because I'm going to show you we can approximate the electric field. So we want a small separation because our approximation is good when the distance of separation is really small compared to basically the square root of the area, right? This is also, in a sense, it's the square root of the area, right? But our approximation hinges on this relationship between the dimensions. All right, so first thing I want to do for you is something of a review. If you have an infinite plane, right? So infinite means it's got an infinite area with uniform charge density, sigma, then what you can have is the electric field has a magnitude that's sigma over 2 epsilon naught, and it is uniform. So what this means is, like, imagine this is our infinite plane, which, looks finite when I draw it, but along the x-axis, say, so if this is the x direction, let's make an assumption real quick that the charge density sigma is positive, then the field lines point away from positive charge, and the electric field in the infinite plane case with uniform charge density sigma, this electric field equals sigma over twice epsilon naught in the I hat direction on the right hand side. But you know that if the field lines point away from the positive charge, then they must point in the negative I hat direction on the back side, right? So this is, you can get this result right here from Gauss's law. All right? So we have this electric field. This also leads to, if you have our parallel plate configuration, right? If we can approximate, or actually, let's do this. This is an infinite plane with charge density, say positive sigma, and this is an infinite plane as well, but with charge density negative sigma. Then in between the plates, the electric field is going to be, so because of the positive sigma, the electric field is this way, and because of the negative sigma, right on over here on the right hand side, that electric field is also that way, right? So this field points towards the negative sigma because it's negative charge, but the other field points away from the positive sigma because it's positive charge. But what that means is that between the two infinite planes, you get sigma over twice epsilon naught plus sigma over twice epsilon naught, right? Which is sigma over epsilon naught. So the net electric field in between the two plates, because of the two separate sources, adds up to this. But out here on the right-hand side, for example, right, I've got negative sigma, so that means that there's electric field pointed this way because of the negative sigma. But because of the positive sigma, I have the same amount of electric field that points in the opposite direction. So over here, the electric field is 0. And likewise, the same story plays out. Because of the positive sigma, I have a field that points away from the charge. Because of the negative sigma, I have a field that points towards the negative charge. And these add up to equals to 0. So uniformly, over here on the right side of both plates, the electric field is 0. And over here on the left side of both plates, the electric field is 0. But in between these two oppositely charged plates, the fields add to each other, right? They combine in a maximal way, and you have sigma over epsilon naught as the electric field between. So our approximation is if D is really small, we'll treat the finite, that is not infinite plates, to have the same electric field as the infinite case. Whoops. So what this means is we're going to take our two finite area plates. So this is area A, and here's another one. Right, this is the edge, the front edge of them, so it sort of looks three-dimensional. Here is the x-axis. And we're going to imagine that even though we do not have infinite plates, we're going to approximate the electric field in between as just being sigma over epsilon naught, where these two plates have opposite charge densities. Remember, the story of capacitance is to imagine separating the charge, moving a charge Q from one plate to another. So in that case, it's like we took Q from here and moved it over to there. And the charge density, sigma, is simply Q over A, right? We're imagining taking the charge Q and uniformly smearing it over the area A, so we have a uniform charge density sigma over the surface of, in the case of the drawing, it's the plate on the right. Because we removed the charge Q from the plate on the left, its charge is negative Q, and so we get negative sigma, which is, or actually we get, yeah, the charge on the left-hand plate is just negative Q over A. So it's going to be a little bit, confusing to write that, so I'm going to not write it, but you know that we separated charge. So we have this electric field, and it is uniform between the plates, right? And what more than that, though, we're also going to continue to approximate that the electric field on the outsides of the capacitor is 0. This is an approximation. The truth is for finite plates of some, finite separation distance d, the electric field actually isn't 0, but it's really small compared to the electric field on the inside. Another thing is the electric field on the inside is not going to be uniform, but it is more and more uniform, or more and more similar to constant, the smaller d is compared to the size of the plates, right? So it becomes a better and better approximation. Engineers would care about these small electric fields on the outside because they're considered stray. And if you have this capacitor in a sensitive piece of electronics, these stray electric fields can alter the outcomes of how the electronics behaves, right? So you have to be careful in engineering settings, but we're doing some physics. We're just sort of seeing what we can have. But it is a good approximation. Yeah. Okay, so if the electric field is sigma over epsilon naught and it is uniform, then the potential difference between the plates, so this is the potential difference between the plates, the way you get it is you integrate the electric field over a path that takes you from one plate to another, right? So I'm going to put in what the electric field looks like in between. This is in red. That's the electric field. So the electric field points to the left in this particular case. And remembering that electric field points from high potential to low potential, right? Remembering this, we can actually sort of do it quickly. Actually, I'm going to leave it in red, but the truth is the potential difference is added up with minus E dot dx, going from one place to a second place, right? So we could, for example, start on the left-hand plate as the first place and go to the right-hand plate as the second place, right, with our dx's. So they're going to deliver us from the first place to the second plate, like that. And so that means that our little dx vectors that take us from 1 over to 2, the dx vectors are rightward pointing, because to go from 1 over to 2, you have to go to the right. And as I go to the right, I'm going to be dotting against electric field vectors that are leftward pointing. And the dot product between oppositely directed vectors is actually negative, but there's already a negative sign, so the negative signs cancel, and this is overall going to be positive in this case. That is, as I integrate up the potential difference, the potential at plate 2 is bigger than the potential at plate 1. So the potential at plate 2 is bigger than the potential at plate 1. And that potential difference is the difference between V2 and V1. But anyways, the integral is simple because the electric field is uniform. And it turns out that the potential difference is just, it's just sigma over epsilon naught times the distance d, right? The distance d is the distance of separation between these two plates. So the integral is simple because the electric field is uniform. In a sense, it's constant and comes out into the front. The dot product is constant, right? Everything's so constant except for moving across the gap using the dx. And that part accumulates up into just the distance across the gap. So it's the distance across the gap times the strength of the electric field, and that's the potential difference. So I'm going to update this. Remember that the reason we have sigma is because it's the charge per area, right? That's what sigma is. And I've got d over epsilon naught as the rest of the constants, right? And remembering that the capacitance, the capacitance is Q over delta V, and this expression right here allows us to calculate Q over delta V. Here is Q, and here is delta V. So let's take this expression that we got to and just solve for Q over delta V. So delta V is Q over A epsilon naught times D. So if I want to solve for Q over delta V, right? So I'll pull the delta V underneath, put the A epsilon naught up top, and divide the D across. So it goes A epsilon naught divided by D, and that's equal to Q over delta V. And this is the definition of the capacitance. The steps were, whoops. Right? So I've presented this lecture as an effort at exploring the capacitance. And the way you explore capacitance is you imagine taking some charge Q away from one of the objects and putting it on the other conductor, right? You have to actively do this. And because you move charge, you get electric field. And because there is electric field, you're going to get potential difference. And the capacitance is simply the ratio of, if you were to move charge Q, how much potential difference builds up between the plates. That's called the capacitance. And that's what this chapter is about. So as you do this exploration, you get ready to explore. You imagine moving Q from one conductor to the other. This is often the hardest step. Work hard to get the resulting electric field. And then number 4 is, once you have the electric field, calculate the potential difference between the two conductors, right, with this electric field. So at this point, what you have is a relationship between Q delta V. You're going to have epsilon naught. You're going to have details about the shapes of the conductors and the separation, right? So Q delta V epsilon naught, and then a bunch of details about the conductors. Like if the conductors are flat with area A, that's a detail that's going to be around. They're going to have some separation distance D. That's going to be a detail that's going to stay around in this relationship. If there's curvatures, then the radiuses of curvature are going to show up as designations of the shape. Something else about the details is how these two things, the two conductors, are sort of oriented with respect to each other. That actually kind of was in the electric field in this case, because the parallel plate had a particular kind of electric field. For us, for this case, it turned out to be uniform. But anyways, once you have this relationship, use the relationship to solve for Q over delta V, which is called the capacitance. And that's it. Okay, so that's the capacitance.